This is Math 30-1 yet again, and we are in Chapter 4 looking at combining functions. Today we're looking at the last section of Chapter 4, which comes back to composite functions, but spending a little bit more time thinking about the restrictions on the domain for the composition of functions. Now, just before we get into today's lesson, before we look at the warm-up, just a quick reminder here about function machines as we looked at in the previous lesson. So we imagined that we had this juicer, which was the composition of a crusher and a strainer. So any input we would choose would first go into this crusher, and then the crusher would crush it up. We'd get, in this case, apple crush or apple sauce or something that would go down into our strainer, and it would strain it out, and we'd get apple juice out. So we said that apples were in the domain for our juicer. We said the same thing about tomatoes. They could go through. Same thing with oranges. They could be crushed, they could be strained, we could get juice out. We said that frogs, just not appropriate to put in a juicer, so we said that's not in the domain. So we'd say that was not in the domain of this crusher because that's just cruel. We're not going to put a frog in there. So we'll say it's not in the domain because it can't go into this crusher. But we did imagine that our crusher was powerful enough to actually crush bricks. So the bricks actually fit into our crusher part, but the output that we got here, kind of in the middle of our juicer, was kind of gravel and powder, and going into the strainer and just gunked it up. So it wrecked the machine at this point. So because it was not acceptable at output at this point, we said it can't be input for our composition, our juicer. Even though it was acceptable for g of x, the output from g of x was not acceptable input for f of x. So there's the review of how we look at this input point, what's acceptable into g of x, what fits in that domain. And then we think about what's the range of g of x. Does that actually fit the domain of f of x? Now let's look at the lesson. And we have these two warm-up questions that I would like you to begin with. So at this point, you can pause the video and imagine that this is a composition of functions, and we want to decide what might g of x be, the inside function, what might f of x be, the outside function. Pause the video at this point, restart it when you're done questions 1 and 2. Well, here I've just indicated the color coding I'm going to use, where f of x is my outside function, g of x is my inside function. There are many different answers we could have to this question. I will show just two that I came up with. Here's one of them. I could say that my outside function is x plus 4. So what I'm doing is I'm saying, well, let's just make this whole thing my x, and then I'll do a plus 4 afterwards. What am I going to stick in place of my x? Well, that will be the g of x function, the 2 times x minus 3 all squared. So there's the inside function that's going to go in place of that x. That is one option. Here's a second option. Suppose I said, well, let's say that my f of x function includes this 2 out here, and then x squared plus 4. So that's all of my f of x function. What's going to go inside in place of the x? Well, that'll be the x minus 3. So there's a second possible answer for question 1. Again, as I said earlier, there are all kinds of different possible answers. Number 2. Here's one possibility. Again, I chose x plus 4 as my starting function, where my inside function, the 2 over x minus 3, that will replace this x in the f of x function. That's one possibility. Another possibility would be, suppose I said f of x is 2 over x, and then I did the plus 4, and now I'm saying that the x could be replaced with this x minus 3, and that would be the inside function, the g of x function. Two of many possible answers for numbers 1 and 2. Well, let's look back at some questions similar to what we did yesterday, but potentially a little more challenging, and then looking at domains as well. So here we have two functions. F of x is the square root of x plus 1. G of x is negative 2x plus 4. As I look at the domain for my f of x function, I remember that the radicand has to be greater than or equal to 0, and so I get that x has to be greater than or equal to negative 1. So here is my domain in interval notation. I could also think about this as, well, this is a square root. It's a principal square root. So since we're given no sign in front, then we actually have a positive sign here. So the smallest we can get in the radicand is a 0. If I plug in this negative 1, negative 1 plus 1 is 0, square root of 0 is 0. But then it can get bigger because we have positives here. So my range will be that x is greater than or equal to 0. And there we have it in interval notation. For g of x, a little more straightforward. It's a polynomial. So the domain and range for both of those, all real numbers. We're asked to sketch the graphs. So square root function, that's like half a sideways parabola. This will be a line with a negative slope. So to save some time, I just did it in Desmos, and this is what my two graphs look like. Question number 5. From the equations or the graphs, we want to determine what is g of f of 3. So that composition, and let me review how we would do this using the graph to begin with. So I'm going to start with my inside function is the red one. And so I want to find out what is f of 3. In other words, if I plug in a 3 into my inside function, remember that's the radical function, what do I get as output? Well, I get this as output. I look across and I see I get a 2 as output. So that tells me I'm looking at, oh, what is, no, I don't want an f, I want a g. What is g of 2 equal to? Well, then I come over here to see, well, when my x value is 2, what's my y value? And I get a y value of 0. So that's telling me that g of f of 3 is equal to 0. And that's how we do it graphically. Let's just clean this up and do the next one, where this time we're going to start with the inside function being our g of x function. So g of 3. So I'll look over here and I'll put in 3. When I plug in 3 into my blue function, I get this as my output, which is negative 2. So this is going to equal f of negative 2. So then I look over here. Let's switch to red, and I see when x is negative 2, what is my y value on the red function? Oh, well, it's not defined. So this 3 was acceptable input in the g of x function, but the output that it gave here, that negative 2, not in the domain of my f of x function. And so here, this doesn't exist. So if we were to look at the composition of functions, we would say that negative 2 is not in the domain of the composition of functions. And in fact, well, we'd say that positive 3 isn't even. Really, that's the point here, that I can't plug 3 into my composition of functions, even though it looks like it fits both of these domains, oops, this domain and this domain for f of x and g of x. Because of what g of x does to it, it gives me an output that f of x cannot take. Well, let's look at actually building this composition of functions. So here the f of x function was the square root of x plus 1. And you'll remember, as I said the other day in a previous lesson, that that x is really just like a brown paper bag. It's a container, and all sorts of things can go into the container. And so instead of actually putting an x in, I'm just putting brackets to represent that container. What am I going to stick in? I'm going to stick in the g of x function. And the g of x function is negative 2x plus 4. So I plug that in, and then I just simplify that expression. Here's what I get. Now, as I come to number 7, and I'm looking for the domain here, I remember that the radicand has to be greater than or equal to 0. So there's my radicand, has to be greater than or equal to 0. And when I go through and solve that, I get that x has to be less than or equal to 5 halves. Okay, so I subtracted the 5 over. Remember, when I got rid of this negative 2 by dividing both sides by negative 2, I had to switch the direction of this inequality. So it became a less than or equal to sign rather than a greater than or equal to sign. And that's because I divided by a negative. So as I look at this and I look back, so x is less than or equal to 5 halves, that's the same as saying that x is less than or equal to 2.5. Well, as we look back here at question number 5, what we were trying to do was we were trying to plug a 3 into our composition of functions. Well, that's not less than equal or equal to 2.5. That doesn't fit in the domain. And so by looking at the equations, we were able to come up with a domain that gave us a restriction that would have told us f of g of 3 would be impossible. Let's look at the next page. Here's the key idea, and we looked at this in the previous lesson. The output of g of x must be limited to acceptable input of f of x if g of x is the inside function and f of x is the outside function. Okay, so we need to have this statement here to begin with. G of x is the inside function. So we adjust the domain of g of x to give this acceptable output. In that previous question, it was fairly straightforward. This question, domain will be a little bit more challenging. So here we have, again, an f of x and g of x function, both radical functions this time. Let me kind of just remind you here as we look at this graph, and we'll review ideas from chapter 2 as we look at finding the domain for this f of x function. So the graph that I just pulled out is the graph of the radicand. So what I have graphed here in green is y equals 4 minus x squared. So 4 would be the y coordinate of the vertex, so that's up here at 4. It's not actually a hole, that's just a space that Desmos gave us. And then the minus tells us our parabola opens down. X squared gives us the shape of the parabola. So you'll notice that the scale is not 1 to 1 here in the sense that it's 1 unit all the way to here, but this is 1, 2, 3, 4 units up to there. So this is at 4 at the top. Well, we're looking at the square root of this function. So what does that look like? Well, you may want to pause the video and think back to chapter 2. How do we find the square root of this green graph? Once you've thought about that, let's think about it. For square root functions, we have invariant points where the y values are 0 and when the y values are 1. So we have an invariant point here where y is 0, invariant there where y is equal to 1. And then I have this maximum, which is 4. I can square root that to get a 2, and I know my graph will go through there. Now again, because I'm drawing on my tablet, this will not be nice at all. But let's see what's going to happen. So I'm going to come down to this point of being below the graph, and here I'm going to be above the graph. Ooh, being really careful, I don't want a vertical line there. You can draw it better than me. Let's try it on this side. So again, when I have a y value between 0 and 1, when I square root it, it actually gets bigger, so my graph goes above the original. But if I square root something bigger than 1, I get a smaller value, so it goes below the graph that I had, and that's pretty horrible. But it gives you the idea. Here we're above, here we're below, and there we're above. So we have this graph. But remember, this isn't to scale, right? This is a 2 here, this is a 2 here, this is a negative 2 here. Oh, this shape is actually a semicircle. We'll get to that graph in a moment, but that helps us with the domain because now we can see that our domain is between negative 2 and positive 2. And our range is between 0 and positive 2. That's for our f of x function. G of x, it's a radical function. And so x has to be greater than or equal to 0. Y also greater than or equal to 0. So there we have domains and ranges for our f of x and g of x. Here, let's look at what this graph actually looks like. So much better than what mine turned out to be. So it is this semicircle here, where I have a minimum value here at negative 2 and a maximum at positive 2. And this y value is up at 2. And here for my g of x function, it starts at 0 and then goes to the right infinitely. Well, here once again, from the equation or the graphs, I'm going to do the graph again. Determine the value of f of g of 4. All right, g of x is my inside function. That's where I'm starting. So if I plug a 4, that's way over here, into my g of x function, what do I get as output? Well, it comes up here and I come across, and what I get as output is a 2. So f of g of 4 is equal to f of 2, because this g of 4 is equal to 2. And that's what I found here. When my x value is 4, my y value is 2 in my g of x function. So then I'm going to look at this, and I'll say if I plug in a 2 into my f of x function, I plug in a 2, what do I get as a y value? I get a 0. So my function is defined for this input value of 4, even though 4 didn't fit into my f of x function. First, the g of x function performed its operation on it, and it gave me an output that fit into the f of x function. Let's look at the two functions flipped. So now if I have g of f of 4, I'll be a little more careful with my colors this time. And maybe I'll erase this stuff over here so we can start fresh. So I'm going to plug in a 4 into my f of x function. Or will I? So there's a 4. My f of x function isn't defined there. So this g of f of 4, again, does not exist. We could have attempted this algebraically as well, and maybe we should do that for this one just to see what would happen. So, well, here we're going to find f of g of x. Well, we're not going to do f of g of 4. So let's look at what did we have there for our f of x function. it was 4 minus x squared, all under a square root sign. 4 minus x squared, but I don't want the x because I'm going to plug in a number there. 4 minus something squared. And the something that I'm plugging in is a 4. So that's this part here. So when I plug in a 4 there, you can already see what's going to happen. I'll have the square root of 4 minus 16, which is the square root of negative 12. This is not a real number. It's an imaginary number, so it's a number that exists, but it's not a real number, and real numbers are what we're working with in this course. So there we're seeing what happens in terms of the equation in the same idea as we had this situation with the graph where we couldn't plug the 4 into that red function. Let's go on to number 11. This time we want f of g of x. So the f of x function, my outside function, whoa, there we go. That's 4 minus x squared. Again, I just left the brackets without the x's. And in place of the x, I plug in the g of x function, which is the square root of x. And what happens? Well, here I'm doing the square root of x, and then I'm squaring it. Inverse operations, they undo each other, so I get 4 minus x. Well, how about the domain? Well, let's begin. Again, I come back here. Remember, to figure out the domain, we need to look at this point. What can go into this g of x function? And then we need to look at this point. What is output that can actually go into this f of x function? So let's start with the g of x function. We already know its domain, and it was greater than or equal to 0 for our x values. Now if I look at this composition of functions, what's the domain for that composition of functions? Well, there we go. My radicand has to be greater than or equal to 0. So this time, instead of leaving the negative x over here and having to switch the direction of the inequality, I added the x to the other side, and then I just flipped everything around. So when I move the x over to this side, it turns into a less than or equal to. So here I can see my two domains shown on the number line, the domain of the inside function and the domain of the composition of functions. Well, here where I say this is the domain of the composition of functions, this is the implied domain by the equation we got up here. So I'm looking at this implied domain and also the restrictions on that inside function, and I have to pick where do these overlap. And so I need to look at this overlapping section, and I can see from here up to there. So my x values can be between 0 and 4, including those endpoints. So I have that limited domain. So here's what I get for the actual domain of that composition of functions. So notice here in red, this was the implied domain from this equation. So I looked at the implied domain here. How is it implied? Well, it has restrictions, so I find what are the restrictions on this equation. That's what I listed. But then I also had to consider the restrictions on the g of x function. Where they overlap is the domain for the composition of functions. So here, let's look at this Venn diagram, because here I've tried to summarize that. So g of x has some limitations, and I'm saying those limitations are in this circle of the Venn diagram, that ellipse. Restrictions on the composition of function, these are what are implied by the equation we're given. And where these two overlap, this middle section, that's the domain for the composition of functions. So this is a bit of a shortcut to make things a little bit easier rather than us having to look at this middle point and say, oh, what's the domain for the f of x function? How do I make that the range of the g of x function? If this is the range of the g of x function, what does that make my new domain of the g of x function? That's fairly complicated. There are times we have to do that when we have a composition of more than two functions, but that's beyond this course. Let me just demonstrate what would be involved if we think of the restriction here on x's, and we make those restrictions on y's, or function values for this g of x function, in the example we just looked at. It's easiest for us to do if we do it from the graph. So I'm going to come back here and look at the graph. So as I look at this graph, I'm going to look at what input values can my f of x function take. Well, f of x can take anything from -2 up to +2. Okay. Now what I'm going to do is I'm going to say, well, what if I had y values for my g of x function between -2 and +2, where would they be? Well, here, my y values only go as far as 0. But then my y values can increase here up to a +2, but then they go greater than 2. So unfortunately, I should have pulled this over a little further, and we'll just adjust these over. Here's that point, and here's this point there. So what I'm saying is the y value of the blue function has to be less than 2. It can't be greater than 2, or I'm going to get a number that's too big to go in. So I say, okay, this is the end. I can't go past here. That's not acceptable, which means I can only use values between 0 and this is the 4. That other one just got moved over with the graph. So we'll erase this one. Okay, so we can see between 0 and 4, my g of x function gives me y values that are acceptable input into this f of x function. That's a challenging idea. So you may need to pause the video, replay this a few times, and think that through. But for now, let me just summarize here at the bottom of the page. To find the domain of f of g of x, the range of g of x must fit within the domain of f of x. So let's just write that in here. The domain of f of x was -2 to +2. Hope we could include those endpoints. That's not very nice. Let me rewrite it. So there, I fixed that, and I've written in the domain for the g of x function. Now, in order to get output here within this set of values from -2 to +2, I had to limit things here. So here again, this -2 to +2, that's restricting what I can put out here. In order to get what fits in here, I had to change this and put it a maximum value of 4 so that I didn't get any output that was bigger than this 2. So to find the domain of f of g of x, the range of g of x must fit within the domain of f of x. So here's the domain of f of x. I work backwards, thinking about, well, if this is the range of g of x, that means I get that range when I limit my input in the g of x function. There we go. So we limit the domain of the g of x function. That's what we did up here. We limited this domain to get the range that we want. This is the range that we want. Now we couldn't get output of -2. Again, as we look back at our graph here, the g of x function, which is the blue parabola, didn't give us any output of -2. So we don't have to fill the full domain of f of x. We just have to make sure that we fit within this domain of f of x. Again, tough idea, standard of excellence, really. Well, the next page gives you some check your understanding questions. So pause the video at this point and work through this entire page. When you're finished the page or when you get stumped, then start the video again and watch as much as you need to, and then pause it, continue, finish off the page, and then finish off the video. So you can pause it now. Well, let's have a look at what I'm getting for answers here. For convenience, I didn't use interval notation. I just said what x and y values could not be. And again, to get these domains and ranges, we need to go back to chapter 2 ideas, where we consider what makes the denominator 0. That's how we find the domain. And where's the horizontal asymptote? In this case, there were no points of discontinuity because there were no common factors between numerators and denominators for the f of x and g of x functions. So f of x in blue, g of x in green. From the equation or the graphs, we want to find g of f of -2 and f of g of -2. So this time I did it algebraically from the equation. So here's what I get for g of f of -2 and for f of g of -2. So both of them are giving me -2 as output. Interestingly enough, oh look, this input gives me that output in this composition. This input of -2 gives me the same output of -2. Curious. Number 16. Here, when I plug in the g of x function into the f of x function, I get this radical inside a radical, which is not very pleasant to work with, but we are becoming pretty good at dealing with these denominators inside of fractions, especially after that trigonometry chapter. I'm going to multiply top and bottom by this common denominator. And so here, these denominators, that denominator will cancel out with this. Remember, this is all over 1, so that's only multiplying to the numerator. Same idea here. When I multiply this into this first term, that's going to cancel out this x minus 1. But it also gets multiplied to this term, and so we still have a 1 minus x when I took this and I multiplied it to this 1. Well, this x and the negative x in the denominator cancel out. I get x over 1, which is just x, which makes sense from what I had up here when the f of g of x, when I plugged in a -2 here, a -2 is what I got out. So whatever I'm plugging in here for x, that's what I'm getting here as output. So f of g of x is equal to x. Well, we're also asked for the domain. So again, there are those two parts that we need to consider. We need to consider the domain of the inside function. So remember that Venn diagram from the previous page. So I'm not going to do the working backwards from the middle. I'm just going to think about that Venn diagram. So there's my domain for g of x. Now I'm going to look at the composition of functions, but I'm not going to look at my final answer. I'm going to look at my original when I first substituted in. So let me move a couple things just to make it cleaner. Okay, so what I've done is I looked at what's in the denominator of this function before I do any simplifying. And so that's what I rewrote here. I wrote that denominator and I said it can't equal 0. So any restrictions at this point have to carry through to the end. So I'm not just looking at my final answer here. In that earlier example we did, there really was no simplifying. And so we didn't have to consider this. In this case, we did a fair bit of simplifying. So we need to look at the unsimplified form, what makes that denominator 0, and I work through the process, and I end up with, oh, that's a little bit too far. There we go. When I multiply this 1 minus x up to the right-hand side, to that negative 1, I get a negative 1 plus x, subtracting x on both sides, and I get 0 equals negative 1. Or near 0 can't equal negative 1. Well, that's always true, which means there are no x values that I have to restrict. So there are no new restrictions for this question. Whew, that's a relief. So the domain is just that x can't equal 1. And looking at g of f of x, it is similar. Here I have my composition of the two functions where f of x is inside. Here's where I'm simplifying, multiplying by that common denominator. Again, I'm getting g of f of x equals x. My input in the original function is the output in this composition of functions. I look at the domain of the inside function, x can't equal negative 1. And then again, I come back to this unsimplified form and look at what's in the denominator. That denominator can't equal 0. So there's my process. Again, I'm getting something like a 1 can't equal 0, so there are no restrictions, giving me this function and its domain x can't equal negative 1. So we had an interesting situation with these two functions, where when I did the composition of f of x and g of x, so f of g of x, they undid each other, and I just got an x out. Same thing with g of f of x, they undid each other, and I just got x out. Well, some bells should be ringing here. What types of functions undo each other? If you said inverse functions, bing, 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 you are correct. So if f of g of x is equal to x, and g of f of x equals x, then these two functions are inverses. So notice that both of these statements have to be true. If just one of them gives you an x, but the other one doesn't give you an x, they are not inverses of each other. So you have to check both. So then we have this notation here at the bottom that says the inverse, the composition of the inverse function on the original function is equal to the original function with the inverse function inside. Either way, they undo each other, and they just give us x as output. One final comment. As I mentioned in passing earlier in this lesson, we could have a composition of 3 functions, or 4 functions, or 5 functions, which really is pushing things for this course. You can expect to see maybe a question or two that would have a composition of 3 functions, kind of like is pictured with that machine function, that function machine that's on the right, where the output of g of x becomes input for f of x. Then the output of f of x becomes input for h of x. And then all of that becomes the output for the entire machine. So we could imagine that that g of x function is my crusher, and the f of x function is my strainer, so I get juice out. And then maybe my h of x function is a freezer, so I'm making popsicles from tomato juice. That sounds delicious. Thanks, Mom. Uh, well, one final thing I'll say. I won't ask you to to find domains when we have a composition of more than 2 functions. So up to 2 functions, we can find the domains, and we're expected to. It is standard of excellence, so you won't see a lot of it, but you should expect to see it. All right, there we finished off this lesson. A little bit longer, challenging idea. but do some practice in your workbooks. Take care.